Hi everybody, it's Mrs. Ellsworth. And what we're going to talk about today is we're going to talk about ionic bonds and also the compounds that they create. Okay, if you remember right, these are compounds, these are not molecules because these ones are ionic. So let's go ahead and get started. Okay, so we talked about how ionic bonds occur between negative and positive ions, that the positive ions are called cations, and I remember it's cation because it kind of looks, T kind of looks like a plus sign, and anions are negative. You can see the similarities there. Anyway, so what happens is that over here, that magnesium had 2 electrons in its outermost shell, and they just got swiped off. Oxygen took them. And so we added 2 more electrons here, and so that creates a negative and a positive charge for each one of these, and they're going to be attracted to each other. So it transferred electrons from one atom to the other, okay, and it made these ions, and so I don't know if calling this a Lewis dot structure is appropriate because now this just held together by attraction, not by sharing those electrons, but just by attraction. And so these bonds are extremely strong. They are electrically neutral. So like if you have this MgCl2, a magnesium chloride, you'll have 2 chlorides that are attracted to 1 magnesium. And so it'll bond together there. They have very high melting points because they are such strong bonds. They're brittle, so they're like a crystal, and so then they can be shattered into several pieces or else powder, and they dissolve in water, and when they do that, they conduct electricity too. Molten ionic compounds, which we can't do that in our lab, we don't have that capability. Anyways, they are very excellent conductors. If you think about it, like when we went and evaporated water from salt, then we had salt molecules that would pop out of our evaporation dish, and that's because, you know, there's still such a strong bond that it holds them together. It's just amazing. Anyway, we started out with looking at some ions. And do you remember that we talked about if it's a negative ion, it'll end in an IDE, and this side of the periodic table over here will have those negative ions? Occasionally, hydrogen could be a hydride if it's towards the back of a molecule too. Anyway, so the IDE means it's a negative ion, and so we look on our periodic table and we notice that chlorine has got a -1 charge, and like I said before, chemistry, we're kind of lazy, we don't write ones, and so it's just a Cl negative. Now magnesium right here is a +2, and so quite often I see it written like this more often than not. Now on the internet, I learned it this way right here, and my professor was old school, and he would go and show me this method here with 2 pluses right there too. So I guess it kind of depends on who your professor or teacher is. Anyway, so fluoride has got that negative sign, but it doesn't matter. You just go over here and you just look up, you see it's a -1, and like I said, we're too lazy to write too lazy to write ones, and so aluminum ion, let's go ahead and look at that one, and it's located right here, and you go up and it's a 3. Now you'll notice it's got a little baby 3 right there too. Well, that just supports it too. But once we get to ions that are down here, we will use a Roman numeral just like what we do over here at the transitional metals. Anyway, so but some transition metals just have a single number 2 above it, like zinc does. So for the zinc ion, we would write Zn and 2 plus or +2. And so there are a couple of them that have that same situation, and you'll notice them, and so you won't need a Roman numeral on that. And when you're naming these ones, I don't want to see a Roman numeral there either. So it's kind of picky, but it is expecting your best. Anyway, the silver ion is on here. I just showed that to you. It's got a little baby 1 on top of the symbol, and so it's just Ag+. Now iron is a transition metal, and it could be a 2, 3, or a 6, so you have to look at the Roman numeral and determine which one it is. And you can't see it on here, but it's a 3, 2, or a 6, but it's almost like you don't need to look that up because it's you know, you already know what the charge is. Maybe you need to look it up just to make sure you get the right symbol, because we would write this as iron 3, so it'd be a +3. And here's iron 6 and Fe plus 6. Okay, so let's go ahead and move forward. Okay, so a magnesium we talked about before, it's a plus 2. And then I see a phosphide here. Don't forget those negative ions have got the IDE, so it's really phosphorus with a negative 3. So we'll go ahead and write those two on here. Okay, so magnesium is a plus 2, and phosphide is a negative 3. And so you can do this charge, adding up charges if you want to, because you know that the common multiple between these two would be 6. And so you can figure out, well, how many does this take to turn into 6? And that'd be 3 of them. And then you could also think, well, how many times 3 would it take to get to be a negative 6 here? And it'd take 2 of them. Or you can just take the shortcut. Okay, and then this comes down here. And it's what we call the switcheroo when you had me before in physical science. And so we put it down here. No charges, right? Because this tells us now how many phosphoruses are here. Okay, and then there's 3 comes down to here. Okay, no charge again because this is telling me what the molecule is. It's got 3 mg's and it's got 2 p's right here, right? So this right here is our magnesium phosphides formula. So you just kind of got to do the switcheroo, and then you can, sometimes you got to reduce these too, so you got to look out for that. Okay, here's another one, lithium bromide. So take a moment, oopsie, and pause this and quiz yourself on that. Okay, so lithium, you should have noticed, is a plus 1. Okay, and bromide is down here a little bit further. It's a negative 1. Okay, and that just works out pretty nifty because it's a 1-to-1 ratio. You bring a 1 down here, you bring a 1 down there. Again, chemistry, we do not write 1s. So it's just LiBr. Okay, LiBr. Okay, aluminum oxide is kind of a fun one. Oh, goodness. And so go ahead and write out their ions and then do the switcheroo, pause it, and then check your work. Okay, so you should figure out that aluminum is a plus 3 and oxide is a negative 2, so I'll go write those out. Okay, so aluminum is a plus 3, oxide is oxygen with a negative 2, and so we do our switcheroo. Okay, the 3 comes down here and the 2 comes down there. Again, their absolute value down here because there is no charges. Okay, so what is that going to look like as Al2O3. Okay. Okay, next is iron 2 oxide. So iron 2, so this right here is telling us that iron has got a plus 2 charge because it's a transition metal that obviously has got more than one charge. So I'll go ahead and write that out as Fe. You may have had to look that up just to see what the symbol is for iron. Okay, it's got a plus 2. How do I know that? Strictly because of this. Okay, oxide is right here. It's got a negative 2. And maybe you can see that this is going to be a 1-to-1 ratio because when you write this out here, it's going to be Fe2O2. And that's a 1-to-1 ratio, 2-to-2 ratio, same thing as a 1-to-1 ratio, so it's just being FeO. And I do expect you to reduce these. So like even if this right here had been a 6, and a 6 here, you'd have to reduce it to 1 and 3. Okay, moving on. Okay, so we have to take a moment here and grab our purple sheets. And we need to just look up these ions on here and write out their ions and their charge. The charge is written right above the ions on our purple polyatomic ion chart. And so if you go look in the very last column, there's a PO4. And then look up at the top of it and you'll see it's a negative 3 charge. Okay, look up the other two, pause this and go ahead and look them up and then we'll check to see how well you do. Okay, sulfate is a negative 2 charge, and hydroxide is one of those few of them that has got no little subscripts right here. And so I think that that might be a reason why it's named with an IDE. I'm not sure, but there's only 2 on this table that have got the IDE, and that's cyanide and hydroxide. Otherwise, anything else that ends in an IDE will be on your periodic table. Okay, so let's go ahead and look at some of these. Now, sodium is an Na. It's in the very first family on the periodic table. It's a +1. And then the phosphate we just looked up is PO4. Oopsie. PO4, and it's got a -3 charge. So then when you do your switcheroo, maybe it's a little bit harder to tell now with more elements in the way. So you get a 3 here and you get a 1 over here. Good. So you get Na3 PO4. Okay, so next one is calcium oxalate. Go ahead and pause the video here and let's see how we did. Okay, calcium, hello, has got a +2 charge. And then oxalate is in the middle column on your purple polyatomic ion chart, and it is going to be a C2O4, and it has a -2 charge. So maybe you can see that these two are going to come down here and that they're going to cancel out, or they're going to be a 1-to-1 ratio. But let's just go look at that for a second. So if it be a Ca2 and then a C, oh, as soon as you got a number down here that's bigger than a, this number is going to come down, it's going to be bigger than a 1. You've got to put that in parentheses so that you know that you've got 2 of these oxalate ions. Okay, anyways, so that, when you look at that, you are not going to ever reduce everything here. Whatever is inside these parentheses will always look like what it is on your purple polyatomic ion chart. It will never change, or else it won't be the same ion. So make sure that you've still got the same formula for your polyatomic ion, even though you have to go and reduce this one. I know you have to go and reduce it, and make sure that you don't go and reduce the 2 and the 4 inside of there, because this thing really is, now it's a 1-to-1 ratio, so it really is just those two kind of scrunched up together. Okay, so be aware. Now silicon is right below carbon. It is an Si, and it's a +4. Chromate, it is in the second family on second column on your purple polyatomic ion chart, and chromate is CrO4, and it's got a -2 charge. Sometimes I think it'd be easier for us to reduce these before they go down, and so I'll go ahead and show you how I do that here. I recognize I'm not even looking at the charges again, because when they go down, they are the number of atoms and we just don't look at them. Okay, do you recognize that there's a 4 and a 2, so it'd be a 2-to-1 ratio? And so this 2 is going to come down right over here, and this 1's going to come down right over here. And since this number is greater than 1, we have to put parentheses around it. Now there's a lot of mess here, so let's go and straighten this all up. You got Si1, okay, and then you got the CrO4, okay, but there's a 2 here, and so we'll do this, 2, okay. That makes sense. You've got 2 chromates attached to 1 silicon. Okay, this right here is one that will trip students. Why don't you go ahead and pause it and try this one real quick. Okay, zinc has got a +2 charge. On your periodic table, it has a little baby 2 right above a symbol, so you don't need a Roman numeral here. Okay, and then it has the hydroxide on there, and you're probably thinking like, oh, hydroxide, that must be on my periodic table because the IDE sound. No, they're one of the 2 of them that are actually on the purple polyatomic ion chart. And so let's go ahead and grab that OH from our purple polyatomic ion chart, and we see it's got a -1 charge. So when you go do your switcheroo, maybe you notice you got ZNO2, OH2, excuse me, and you're thinking like, oh, well, gee, that looks fine, but it's not. You actually have 2 hydroxides attached to this thing. So the zinc has got 2 hydroxides on it. Even though you don't have a number there, it probably feels